Good day, everyone. I'm going to spend about 10 minutes to introduce our research about robotics. First, I will give a brief introduction to myself. My name is Po-Chiang Lin. I'm currently an assistant professor in the Department of Electrical Engineering at University. Our research interests include robotics, AI, machine learning, and deep learning. What is mobile computation networks, and finally, maker and STEM education. Before I went to serve in University, I have several years of work experience with the Six Tech Corporation and the Coast Group Telecommunication. Later I find out that the Coast Group Telecommunication is merged by the Far Eastern Telecommunication. So, but at that time, I don't have the opportunity to join Far Eastern. But finally, I'm here in Yuanji, so I'm part of the Far Eastern group. Our research is about spatial AI for robotics. First, what are robots? I think that different people may have different definitions about robots. But for me, I think that robots are data-driven machines. Why? Because these robots will acquire data, process the data, and act based on the data that they collect and process. So here on the right-hand side, you can see the figure. That is a classical three-tiered architecture for robotics. So here we have three layers: behavior control layer, executive layer, and the planning layer. Our robot usually uses the sensors to get some information from outside the world. And finally, the robot will make some decision and try to finish some tasks, finally to pass the decision to some actuators, such as the motor, to affect the outside world. And at the second layer, that's the executive layer. So here we have memory interpreter try to accomplish some tasks here. Finally, about planning, that's pretty like our human's brain. So here we need some persistent information and try to make some long-term decision. So here, let's go back to spatial AI. Spatial AI try to enable the robots to perceive or to understand the spatial information about the whole environment, including the objects, the things, and the environments. And then after that, after we have the spatial information, we can use that for intelligent decision making and planning. There are several applications about spatial AI, such as the robot navigation, self-driving car, AR, VR, and so on. Here I'm going to show some examples about our previous work. The first one is the co-work with a robot company in Taiwan. We try to help to design some robot applications. The first one is about STEM and navigation. STEM means simultaneous localization and mapping. That is a classical and important task for robotics. So we can see the robot locates here in my office. And from the map, we can see that the robot actually locates here, which is consistent with the actual environment. So on the map, we can click here to denote the destination location and the direction. So you can see we have a green path. That's a path generated by the algorithm. And finally, the robot will follow the green path and move to that destination post. And of course, we can click the other destination post again. Okay, that's the first example. In the second example, here we try to design another robot application for human following. So after we run our program, you can see that the robot locates here. The robot tries to use the camera above to detect the human. That's actually me. The program will let this robot to trace the human and to keep the distance between the robot and the human for almost 1 meter. And recently, I co-worked with one of my master students to work out this research about point cloud classification. So here, I think maybe some of you are not familiar with point cloud, so I will try to give an example here. This figure shows an example about point cloud data set. So there are several points here. Actually, the point cloud data set consists of the data like this. Each row means one data instance. So each row means one data point here. So how do we represent the point cloud? We can, of course, use the three-dimensional coordinate, for example, the x, y, and the z coordinate to represent one point. And sometimes we can also use additional information such as the normal of that point to the surface. So again, we can use the three-dimensional coordinate to represent that normal. So usually each instance consists of 3 numbers or 6 numbers. And for one object, it usually consists of maybe hundreds or thousands of point clouds here. So point cloud data classification is to determine that once we get the data like this, we want to classify what this object is. But I think for most of us, maybe we all have some difficulty to determine what this is. So let's try to take a look of this object from the other side. Okay, I think now that's better, right? Maybe you can classify this maybe like a brush or a guitar. Let's take the other look from the top view. I think that's much better, right? As a guitar.
Guitar.
Right.
Yes.
Right. All of the 3 figures represent the same object. So I think you can try to design or invent many different kinds of creative methods to try to classify this object. So from the literature, there are already several methods to try to use different kinds of creativity to perform this point cloud classification test. And recently, I worked with my master student, try to design a new algorithm. You can see that we can get a better classification accuracy than the other previous works. Based on the current achievement, in the future, we are going to try to extend our work about point cloud. In the previous slide, we talked about the point cloud classification, but we still have some other tasks to do. One task is called the part segmentation. For example, we have a point cloud like this. Since that we can already classify this as a chair, we want to further segment the point cloud here. For example, we want to segment this part to be the back of the chair. This is the seat, and the others are the legs of the chair. This is for part segmentation. And the other task is the semantic segmentation. For example, suppose that our robot locates here, maybe at the door of one office like this. So the robot can use the sensors, for example, the LiDAR or the depth camera to sense the environment, the whole office. So you can see that there are several point clouds here. Of course, for we humans, we can see that these 2 are the chairs. There is a partition here, there's a desk here, and with some bookshelves here and a window here. But for robots, this is a difficult task. So we hope that in the near future, of course, if the Indian students are interested, we can co-work together, try to invent some algorithms to segment all of the point clouds. For example, the 2 chairs to denote it as red and so on. In our lab, we have several robots, such as the wheeled robots, and we also have a huge robot like this. We also install a collaborative robot arm over it. So I think that is suitable for both indoor and outdoor environment, and also suitable for agricultural applications that Lin just mentioned. In addition to the field robot, we also have some humanoid robots. They are all interesting. There are small-sized, medium-sized robots, and a huge robot with an Intel NUC computer inside that and a camera there. So we can also design very interesting applications, such as face detection, or to ask the robot to detect the football and to kick the football. So maybe some of the students are not familiar with robots or the so-called robot operating system. So we also design some courses and the workshops to help students to get familiar with this. Okay, so I think that is all of my presentation. Thank you very much.